illustration is an example of an orbit. A man-made satellite orbit around the Earth. Now, what is the significance of this one? This is a kind of puzzle. Let us start our discussion with the billion-dollar puzzle to be solved later. Ground Controller C is a remote control operator of satellites A and B. Satellite A is 1,000 kilometers ahead from satellite B. Satellites A and B are moving at the same speed, orbit, and altitude. Control operator C plans to overtake Sat A by Sat B. What do you think the control operator C would do to execute the plan smoothly and perfectly? Telescopes and NASA. From the Dutch perspective glasses of Hans Lippershey, followed by the design of Galileo Galilei's telescope, there came an enormous upgrades to what are now known as the Hubble Space Telescope and Kepler Space Telescope, to name a few. These telescopes open our view and give us clear understanding to what the deeper universe is keeping in. The progress in space exploration is catapulted by NASA's great technology, although Russia pioneered the first Earth orbit with its Sputnik 1. The satellite space telescopes, moon missions, the two space probes, Voyager 1 and 2, and the Mars probes are extremely valuable assets for the greater understanding of the universe. Telescopes. This is the James Webb Telescope, space telescope that will replace the Hubble Space Telescope. There are numerous telescopes now in place. Two of them are the Hubble Space Telescope, HST, and Kepler Space Telescope, KST, that are in orbit. Atacama Large Millimeter, Sub-Millimeter Array, or ALMA, Arecibo Observatory, Carl G. Jansky Very Large Array, WM Keck, and Palomar Observatory are in place in the strategic parts around the world. Moon missions. Lunar roving vehicle on display at the NASA. Astronaut picture taken. Several moon missions were carried out, and the most famous is the Apollo 11 first moon landing and man's first step on the lunar soil. This paved the way for the space age. The moon landing success was followed by numerous lunar rendezvous, including driving of the lunar roving vehicle on the surface of the moon. Although there were some major accidents happened along the way, the space exploration benefit to mankind is still enormous. This is the artist depiction of the Voyager. Since the launching of Voyager 1 and 2 space probes in 1977, more than 40 years now, still, the space probes continue to send data back to Earth. Voyager 1 and 2 exited the helipause, the place where Sun's constant law of materials and magnetic field stop affecting its surrounding, and are now in the new region, the interstellar space. Red Planet Probe. Since the early 1960s, a lot of spacecrafts, mostly from US and Russia, have been sent to investigate Mars. And in 1998, Japan joined the exploration, but their spacecraft failed to enter the orbit. After this try, few other countries follow suit. Today, there are two spacecrafts operating on the Red Planet, the Mars Science Laboratory and the Mars Perseverance. Origin and history of telescope. The telescope is one of the most important inventions for the modern astronomy. However, little is known about how the idea of telescope originated because the identity of who really invented the device still remains a mystery. It was Hans Lippershey, a Dutch eyeglass maker, who in 1608 first applied for the patent of the device. Controversy spouted that even other personality was claiming that the telescope was their invention. A few weeks after Lippershey applied for patent, Jacob Matthews applied also, but both applications were rejected because of the counterclaim issue, and that officials from the Dutch government argued that the device was easy to reproduce, making it difficult to patent. To further fuel the controversy, others were saying that Lippershey just stole the design from Zacharias Janssen, another eyeglass maker who happened to be Lippershey's town neighbor. But the accusation did not sit well with the scholars who argued that there is no real evidence that Lippershey did not develop his telescope independently. With the scholars in his defense and with his patent application, although denied, Lippershey still got the credit for the telescope, and he was paid by Dutch government just to produce more of the device. Janssen, meanwhile, was credited with inventing the compound microscope. The news of the telescope spread all throughout Europe. In 1609, Galileo Galilei probably already had the idea of the telescope, although he did not see one, that within days upon hearing one of the news, he was able to design his own telescope that could magnify objects 20 times. He then presented it to the Venetian Senate and in turn set him up for life as a lecturer at the University of Padua, with his salary doubled. With this telescope, Galileo Galilei was able to discover the rings of Saturn, sunspots, and four of Jupiter's moon, to name a few. Astronomical Unit, or AU. 152,100,000 kilometers, farthest distance from the Sun to Earth. 147,300,000 kilometers, shortest distance from Sun to Earth. The unit of length, defined as the average distance between Earth and the Sun, which is about 149,597,870.7 kilometer. The astronomical unit is used primarily for measuring distances within the solar system and other nearby stars. Light year. The distance traveled by light moving in a vacuum in the course of 1 year at its accepted velocity of 299,792,458 meters per second, or 186,282 miles per second. That is the distance traveled by light 1 year. So this is the light year. A light year equals 9.46073 times 10 kilometers, no? Or 63,241 astronomical units. Parsec. Unit for expressing distances to stars and galaxies, used by professional astronomers. It represents the distance at which the radius of Earth's orbit subtends an angle of 1 second of arc. Thus, a star at a distance of 1 parsec would have a parallax of 1 second, and the distance of an object in parsecs is the reciprocal of its parallax in seconds of arc. We will not be going to understand parsec without understanding the parallax, and later on we'll discuss the parallax. 1 parsec is equals to 3.26 light years, which is equivalent to 3.09 times 10 kilometers. Now this is the parallax. The difference in direction of a celestial object as seen by an observer from two widely separated points. In this case, the Earth and Sun. So let's say there is a person observing on Earth, and also there's person observing on Sun, which is impossible. So one astronomical unit is 1 arc second if we are talking of the parallax. So see, the view from the Earth and the view from the Sun when they are watching the star. So this intersects and form an angle. So the distance from the Sun or Earth to the nearest star they are looking is 1 parsec. So see, they intersect their view. No? That is why that is the apparent motion. Apparent parallax motion of near star. Okay. Let us compute. What is the parsec of star Sirius when its parallax is 0.37921 arc seconds? Formula: parsec is equal to 1 arc second over parallax. Solution: parsec is equal to 1 arc second over 0.37921 arc second. Is equals to what? 2.64 parsecs. So that is the parsecs for Sirius. Okay? Star Sirius. Sirius is the brightest star that can be seen by the naked eye. Major axis. The maximum diameter of an ellipse. In this case, the maximum diameter is in vertical position. So we are going to take that maximum diameter. Okay? So that is the major axis of an ellipse. Semi-major axis. Of course, this is half of the major axis of a conic section such as an ellipse. On Earth, it is the equatorial radius. Remember in your previous lesson about science, about Earth, the shape of the Earth is oblate spheroid. So it is bulging at the equator and flattening at the pole. So if it is bulging at the equator, then this is, we take the radius of it as a semi-major axis. In this case, this is the illustration. Have a look. Okay, that is a semi-major axis. Semi-minor axis. What's this? Radius from the center of an ellipse to the maximum flattening. On Earth, it is the polar orbit. Again, the shape of the Earth is oblate spheroid. Bulging at the equator, flattening at the pole. So that is, we take the radius of that from the center of the Earth to the pole, and that is the semi-minor axis. Okay? The illustration will show you. See? That's it. No? Two semi-major axes. Radius, that is the minor axis. Focus, plural, foci, one of two fixed points inside an ellipse from which the sum of the distance to any point on the ellipse is constant. Take a look. There is a point. That is one focus. Another point. Another focus. So the two is actually the foci. Ellipse. Symmetrically shaped closed curve for which the sum of the distances from any point on the ellipse to 2 points inside is always the same. We explore a little of geometry and drafting class. This is how to manually draw the ellipse, and because the ellipse is already drawn, we will just prove whether these two distances originating from the foci or two focuses to any point or the edge of the perimeter of this ellipse will always remain equal. Okay? This is line A and line B. The distance of line A is 5. Let us say, and this is line B is also 5. 5 because this is at the middle, no? Of this point of this perimeter. The sum of these two lines, 5, 5 is equal 10. If I move this pencil to this point, let's say here, line A becomes 3 and line B becomes 7. Line A decreases, line B increases. 3 and 7. If you add 3 and 7, the total remains 10. Now, let us move further the pencil to this point. Let us say here. Line A further decreases and line B further increases. Line A is now 1 and line B is now 9. To add both lines, the sum total will remain 10. Now, let us see whether the pencil will always point to the perimeter of the ellipse. If this is so, then this is the definition of ellipse. Let us begin moving. Okay? Okay. Now, okay, put here. See? So the pencil points always to this perimeter. No? Nothing goes here and here. So this is ellipse and this is the definition of ellipse. The eccentricity of an ellipse is a measure of the amount by which it deviates from a circle or how flat or round the shape of the ellipse is. Geocentric Earth. Any theory of the structure of the solar system or the universe in which Earth is assumed to be at the center of it all. Sun and all planets moving around the Earth, that is the geocentricity. The most highly developed geocentric model was that of Ptolemy of Alexandria. However, geocentric idea proved to be wrong in the advent of heliocentrism. Geocentrism became applicable only to natural satellite, which is the moon in the case of Earth, and the nearly 6,000 man-made satellites orbiting Earth. That is the moon, and that is the orbit of moon. These are the orbits of the man-made satellite. So that is the man-made satellite. Heliocentric, Sun as the center, or heliocentrism, a cosmological model in which the Sun is assumed to lie or at near a central point, exempli gratia, of the solar system or of the universe, while the Earth and other bodies revolved around it. So this is the Earth revolving around the Sun. Aphelion, the point in the orbit of a planet, asteroid, or comet at which it is farthest from the Sun. In this case, aphelion is 152,100,000 kilometers. Perihelion, the point in the orbit of a planet, asteroid, or comet at which it is nearest from the Sun. That is the Earth, that is the nearest one. What is that? That is 147,300,000 kilometers. From the word helion, sun. Aphelion, apo, means far. Peri means near. Orbital period, the time it takes an object to travel once around the Sun. In the case of Earth, it takes 365 days or 1 year to complete its cycle around the Sun. orbital speed. That is the speed when traversing the orbit. The speed at which an object orbits around the mass of another object, in the case of Earth, revolving around the Sun at a speed of 107,208 kilometers per hour. Orbit, the path of an object that is in revolution about another object or point. In the case of any planets or any heavenly bodies moving around another body, this is an imaginary celestial road. If on Earth there are numerous asphalted or concrete roads, in space there are imaginary celestial highways. Revolution. The movement of an object in a circular or elliptical course around another body or center. Okay. How about rotation? It is the movement of an object in its own axis. Now let me give a demonstration. In this demo, we will show to you what is revolution and what is rotation. Let us say this ball is the sun and this golf ball is the earth. Actually, the size of it is comparable to Jupiter because Earth is 109 times. The Sun is 109 times bigger than the Earth. But because we don't have any ball, let us see. This is the Sun, and this is the Earth. So, this is revolution. Revolving around a body. Okay? Now, this is rotation. Okay? On its own axis. Moving on its own axis. While revolution is like here, like this. Okay. Okay. See? Now, to give you a clear view of what's happening between the Earth and the Sun, the Earth is rotating counterclockwise when viewed from the north of the Sun. So see, this is the Sun, and I'm looking at it. So this is how the rotation of the Earth goes, counterclockwise, and the movement also, the revolution, is counterclockwise also. Counterclockwise rotation, counterclockwise rotation. Okay?